It's always fun getting going the first night. I think Will already introduced himself, maybe. Okay, well, we'll start.
Perfect.
Timing's everything.
Good evening, I apologize. No worries, no worries.
My name is George Carey. Work here at FIA along with my colleague, Will Fisher. And you'll get a chance to see us for the next 4 weeks. Talking obviously the subject of hydronic system design, some of the fundamentals, and we'll get into that and all the details. I guess a little house cleaning. Men's room upstairs on the first floor here, right? And then the ladies' room is downstairs in the main office. In addition to Will and I here, we have a couple of FIA employees. So Matt Thomas, Brad Parnell, and Craig Hatfield. So if you have any questions or need any help, don't be afraid to ask one of these gentlemen. We'd be more than happy to help you out. We have, I think it's lobster tails and drawn butter coming tonight for dinner. We'll have, what do we have? Panera coming tonight. So we'll stop probably about 5:15, 5:30, grab a quick bite. We'll pause, and then we'll come back in and continue until around 10 o'clock tonight. But anyways, it's a combination of obviously everyone here that's live in person, and then we've got three or four remote virtual. So where I've got my AirPod going, speaking, Will's checking in with them. If they've got a question, they can go to the chat room. We apologize again for just that first introduction, or first getting this thing going here. Hopefully it'll smooth out. It usually does each year once we get going. I thought I'd just start with a quick introduction. Again, my name's George Carey, Will Fisher, a gentleman that's behind the scenes, kind of will coordinate a lot of what we present each night. We'll have a PDF version of it that will load up into Dropbox. And actually, David has everybody's email address, so he'll load it up and give you the link so that in terms of the PowerPoint presentations, they'll be listed as a PDF copy if you're so interested. Those that came here tonight in person, obviously, you're going to have the Bell and Gossett design manual, which is pretty powerful stuff, regardless of name. I mean, obviously B&G, we're the B&G reps, but everything about it is just fundamentals, and it's all physics or math, Mother Nature, how things work, regardless of the manufacturer's name. So anyways, this class has been going on for a long time in various iterations over the years, but speaking to the engineering community about hydronic system design. And I've been doing it a long time. Let me see here. I should see if I can put this on. Let's go back here. Not sure why, but anyways, just real quickly. And Will, you can still see those slides. Yeah. Remote. Okay, good. So Bell and Gossett years ago, 1954, opened up a schoolhouse, a little red schoolhouse, and they truly built a little red schoolhouse out on their campus out in Morton Grove, Illinois, just outside Chicago. Tens of thousands of people have come through that facility. When FIA opened up, again, years ago, we've been here as a representative of the company since 1964, so 61 years in New England here. And so it's been around a long time, but we tried to bring what they do out there to the East Coast. So right here in New England. So this is, the 60th version, if you will, of what's been going on over the years. So they kind of promoted and pioneered the education and the promotion of hydronics. So this is just the next generation, if you will. Just getting fundamentals. You guys are all probably varying mechanical engineers. And now you're taking a deep dive specifically into hydronics and pumping and all of those accessories and boilers and heat exchangers and everything associated with chilled water and hot water and all that. So we just want to, kind of help you along, give you some information. Like we said, it's the fundamentals. It's not a super deep dive, but and just a review, you would have seen this in probably the original email that Will had sent out, but each week and the 4 weeks listed. But we'll start with just a little bit of hydronic system components, what you're going to see in a typical system, small, big, large, anywhere in between. We'll talk about pumps and then get into pump curves and system curves and that kind of interconnection or interrelationship. I don't know how much time I'll have at the end. We might try to touch a little bit on that system Syzer, which was that calculator that we passed out. Everyone's got a copy of it. Second week, we'll get into, some applications, variable speed pumping, pump affinity laws, ECM pumping, etc. Third week, Will's going to take over and kind of dive into heat transfer, heat exchangers, and then get into a little bit what's happening within the industry. A lot of changes with electrification, decarbonization. So heat pumps and the role that they're starting to take over in this industry. And hybrid systems where maybe we're combining or designing around legacy gas-fired equipment perhaps, but then adding electrification, heat pumps, air source, geo, whatever the case may be. And then the final week, the fourth week, we'll step back into a little bit of primary, secondary piping. So some of the common piping applications that you guys or your offices are probably already instituting, but just give you kind of a nuts and bolts of what it's all about, how to apply it, especially as you start getting into that week before that hybrid system, when you're talking and you're kind of combining different technologies and different heat sources and cooling sources. Air management, expansion tanks, and we'll kind of round it off. So you'll kind of get a pretty good flavor of, again, back to those fundamentals. And again, these books are for you to take. Obviously, you don't need to bring them back and forth each week. We're not going to ask you to sit and open the books and play along, but just recognize that a lot of this subject is from those books. And C-note, is that correct, C-note? C-note. You had mentioned earlier, Gil Carlson, so famous engineer. I might repeat myself a bunch of times over the next few weeks about that gentleman's name because he did have his handprints all over every book that's in your manual. He was kind of a famous engineer from B&G that played a big role in ASHRAE and helping design and come up with different standards and different principles. We'll talk a little bit about that. But these books are very, very useful. The manuals. See here. I want to go to is that showing up as the presenters? Oh, dude. So you're seeing that differently now. I gotta, clean it up on this end. I'll try to. Did it just go back? Let me try it. Okay, good. So just jumping in, hydronic system components. What is going on with this clicker? Got a little piping layout here. Boiler room, multiple boilers, piped in a primary, secondary orientation. And with that, distribution pumps, air separators, expansion tanks, flow control valves, domestic hot water production through an indirect water heater, individual boiler pumps, etc. That's a pretty standard mechanical room. Commercial space or, and those B2, the size of those boilers, they could be 3-4 million BTUs each. You could be looking at a pretty good plant. You could be looking at a little smaller, maybe a dormitory or a gymnasium, whatever, on a college campus. So just understanding the fundamentals of how that all works, how to lay it all out, and how to select the various components that you're going to need for that application. That's pretty standard. Couple of snapshots. This one's just out of a, it's taking that line drawing. This is it in the basement somewhere at some commercial space that, an engineering firm would have specified it. A job went out on the street, contractors bid on it, get awarded, go ahead and go do the work for the GC who's doing the renovation or whatever, the new construction. So we've got some high capacity, X number of million B2 boilers. We've got our distribution pumps, the boilers themselves, which is kind of hard to see in this picture, but they have their own pumps. So we're doing kind of that, what that picture back here would have shown primary, secondary, with each boiler having its own pump. So, that's the stuff that you're going to see. That's what we deal with on a day-to-day, day in, day out. Another technology or another methodology would be, instead of primary, secondary, they get into this thing called variable primary flow. And you'll have your distribution pumps, but you'll notice, and you have your boilers, but perhaps we don't have primary, secondary. We don't have individual boiler pumps. We're using distribution pumps to flow through the distribution, but also the boiler plants flowing through our heat sources. And that can get a little finicky, a little tricky. It's done, it's out there. Manufacturers approve it when it's done right, but it's just another technology you want to be aware of. Here's maybe just a little bit of an exploded view where we're doing it out to a building, variable primary, through the boilers out to our terminal units. And those terminal units could be buildings, depending how big the system is. Each one of these takeoffs could be a building, perhaps. Maybe we've got some kind of VFD drives, variable frequency drives, with remote sensors to feed back to the drives to influence the speed of the pump, the energy draw, how much kW, as we can ramp down that horsepower, that electrical draw. So again, just different technologies. Here, it would be taking primary, secondary, and kind of put it on steroids a little bit. And what I mean by that is, this is actually, again, just a line drawing, but it was actually one of the airports. I think it was Denver International X number of years ago. And what we got going on is you got a chiller plant over on the left-hand side. So they got their own pumps, almost like the primary, if you will. And then you've got these distribution pumps that are feeding what looks like, these other zones, if you will. Those zones are terminals at an airport. So a fairly big, job, pretty big layout. And so, we'll get primary pumps feeding. So you'd have primary, secondary, tertiary, might be the term that you'll hear, primary, secondary, tertiary. And again, with all kinds of controls feeding back to influence speed of zone pumping as zones are opening and closing, parts of a building open and closed, loads change. We can change flow rates on our tertiary pumps. As flows change across our crossovers, we can change our distribution flow rate. There's a lot of stuff going on there. So from a very simple little boiler room to a pretty complex, large mechanical layout. And again, it's what we get involved with. We've been doing it for years. That's our job, is to get involved with the engineering community on how to lay this out, whatever job it actually is. As we start to embrace some of that new technology, here's a quick example of mechanical layout where we're talking air source heat pump chillers. And we're combining them with, say, legacy. So we've got some natural gas high efficiency appliances on this drawing. And then we're combining that with, buffer tanks, and then we've got distribution pumps, we've got air separation, we've got expansion tanks. So we're kind of taking the best of both worlds here, or not the best, but combining different technologies where, as the market's moving in that direction, so to speak, where this air source heat pump chiller can provide hot water during the winter to a certain extent, and then certainly chilled water all summer long. And then at some point when it gets really cold and that air source maybe, isn't working at peak performance because of the outdoor conditions, we start to bring on our legacy, our gas system, to supplement and provide the water temperature that is needed for this, maybe 100, 200 unit, complex, multifamily layout or whatever. So that's pretty common. You'll see the expression two pipe. And what's happening there is it's either heating or it's cooling. So in the summertime, we're cooling, the winter, we're heating, and then they're going to pick a magic date in the fall and in the spring where things switch from either heat to cool or cool to heat. It's not a four pipe system. That's a different layout. But a lot of this is where this is kind of becoming popular is retrofits, existing buildings where they're trying to upgrade to this decarbonization or electrification push or drive. We can help them mechanically design and lay out and then select components to make this whole thing work. Here's just one last, I think it's just one last, again, it's a drawing from another engineering firm, but we're saying, hey, we've got multiple sources of energy. We've got air source heat pumps. We've got heat recovery chillers. And then we have our traditional condensing natural gas-fired boiler plant. So we've got a pretty big, I mean, 20 million BTU plant. It's a good sized plant. And then we're saying, hey, how do we, and we can talk about, we can grab energy from the heat recovery. We can grab energy from our air source heat pump until an outdoor temperature, until a certain point. And how do we have all of these different sources all kind of coexist without fighting each other, different pumps and all of that? And it's quite simply with some of these very closely spaced T's, these primary, secondary connections with this 4 boiler or 5 boiler plant. And then we've had, we've got our main distribution air separation expansion tanks and our distribution pumps going out to a campus, so to speak. It's a lot. So it's just another example. So these are the things that you're going to see, you're going to bump up against in your career, especially all you young guys and ladies. This is not going away. This is becoming more and more popular, becoming more and more common. So the first up, again, B&G rep, been around here for 61 years. So pumps, and it expands from there. But start with centrifugal pumps. So just quick snapshot, different style pumps. You got inline pumps, base mounted, double suction, vertical split case, horizontal split case, fancy terms. They all kind of mean something, but inline, we'll show a couple of the pictures of it, but they're in the piping. They're inline in the piping system, inline. You have vertical, you can have horizontal on those inline. You get into base mounted. So I have a pump mounted on a base, end suction. I have the entrance to that pump is at the end. The suction point of that pump is on the end and the discharge is out the top. And then when you get into some of the bigger applications and the higher flow rates, this style pump is going to be very common, this double suction vertical split case. And then there's all different orientations. So a little smaller, lower capacities. So lower flow rates, smaller pipe sizes. You get into bigger, probably going to base mounted. And at some point, you actually will exceed his capacity or its capacity. And that's when you're going into these much bigger double suction pumps. Yes, sir. So end suction here, discharge out the top. What happens is, and we'll talk about the same thing will hold true here on this vertical. And I'm jumping ahead, so we'll get to it, but double suction and what that all entails, you're going to have a wider opening on the suction side, if you will, entering into the eye of the impeller or, and then discharge out either horizontally, or in this case, the orientations are vertical. That's a good question, though. It's important to know when the guys are piping it, the fitters, they got to know, right? And there's castings and all of that, but it's a good question. There you go. That's a good point. Yeah, coming down. Because once you start to see what the impeller looks like, it'll make perfect sense how it sits inside. Any one of these wet ends, they'll call it like a volute, is the term they'll use, the pump manufacturer will use. So just a quick definition, a centrifugal pump. So a pump mechanism to push liquid with a specific force to overcome system frictional loss and then any existing elevation differences. A centrifugal pump, which is what we deal with, that's what we sell, centrifugal pumps. It adds energy in the form of velocity to flowing water. The pump produces the velocity through the means of a motor, which consumes energy in the process. So as that motor is spinning and creating revolutions and the impeller is spinning and it's imparting velocity to the water, and there's a cost, there's an energy cost to that. How much energy do I need? How much horsepower, etc. But that's the pump that we're selling, the pump that you guys are typically designing around when we're talking chilled water and hot water heating. And it's kind of it's a little cartoon drawing, but all I was showing is you had a can upside down on a shaft and with no rotation, it had little holes in it, water would drain out and just be a function of the static weight of the water, atmospheric pressure pushing down. But if you were to cause rotation here and spin it, and you create this velocity, that can would unload a hell of a lot faster, just adding velocity to that water, energy. When you look at, in this case here, it's probably more of like a base mounted pump, not limited to. All of the pumps will have some version thereof, but an end suction where you have this impeller that's sitting inside this end of the pump, this volute, and you have what they refer to as the impeller eye. So that's the eye. It's where the water enters into the impeller. Then you'll have these veins where we're showing them impeller veins. They'll kind of highlight. They're kind of curved. It's all engineered. I mean, there were engineers, just pump manufacturer engineers that just design pumps, how to make them the most efficient and based on horsepower and capacities and all of that. But these veins add, make the impellers perhaps more efficient. And depending upon the size of the impellers, they could be thicker or they could be wider diameter for more flows, etc. But you're going to have this impeller attached to a motor somehow. And that motor is going to spin. It's going to cause this guy to spin. And that, as that water comes into that eye, it gets flung along these veins. And that's where the velocity gets added. And as it gets added, it's rotating inside this casing. And this casing slowly gets wider by design. And that velocity gets converted into pressure differential. And that's that high pressure going to low pressure. So anyways, we're not building pumps. I just want you to know what it looks like on the inside. So the veins, the impeller itself, a suction eye, you got to cut water. The main thing is that proper rotation in the impeller is such that if someone was to visually look at it as it's spinning, it'd say, geez, those veins are kind of slapping. And that's the proper rotation because the water's coming in. And as it's spinning, that water gets flung along those veins and gathers inside the outer edges of that casing in that volute. Just more of the same. Am I going the wrong direction here? This is my, sorry about that. So single suction. The most important, in terms of that term, single suction impeller, that drawing on the left-hand side. I have an impeller on its horizontal. I have a piping on that left-hand side that's entering into the eye. That's how the water gets into that impeller, in that eye, single suction. And these are just different pictures of different orientations of say a brass impeller that you might find inside. Although a lot of the manufacturers and a lot of the applications might be going to stainless steel material today. Brass was very popular for a long time. Excuse me. So this opening here, oh, I'm sorry. In is going in, yeah. And that's a probably a fairly decent capacity volume. So it's got a wide or a large diameter eye, but the water is heading this way in and it would enter into those veins, just like kind of that cartoon drawing, and it will get flung and it'll get to the tips of these And that's where the velocity is the highest, is as it gets flung out, and it gets to that tip, and then it gets gathered in that casing and gets directed, discharging out into the bottom, spun around, discharged out, coming this way, up into the suction, into the eye. So that's why that hump, that bump that we were just talking about, was a good question you asked. Wherever that bump is, that's what's directing the water into the eye, because it's got to get in and then spun around and then discharge out. Bonus question. Whoa, early. Oh, that's a good question. I think I got a decent picture. Yeah. Yeah, correct. As this is spinning, right? And that's what they're talking about. Rotation, right? Is going this way. And the water's being flung along those tips, gathered here, and discharge out. One of the things I didn't mention, they'll mention this name, a cut water. And we'll have examples a little bit later on tonight, I think around 9:30 or so. And a manufacturer will make this like a commercial pump. And they'll have, like they call it, a full wheel. So the largest diameter impeller they can get in there and have it work properly. But sometimes that might be too big. I don't need all of that. So they'll trim it. So they trim the impeller down and they'll go to a certain range. But then at some point, you can't make it so small because the high percentage of the water that it's spinning using the motor horsepower, the electricity, would just recirculate. So it'd be very inefficient. So they have this cut water, and that's kind of that dimension. That's that go point right there. When that water's coming around, am I going this way? I want the majority from an efficiency standpoint. All that energy I used to spin that impeller from that motor, I want that water discharging out to the system. That's what that cut water is there for, that's the break. There's always going to be a small percentage, but we want to keep it small. Not that we have a lot of control. The manufacturer tells us. They test it. So this is the cutaway of that vein, of that single suction impeller, what it might look like. They would have taken it at the shop and probably just cut the cover right off it. Kind of interesting look from there. So here would be like the shaft would be coming in this side, and this would be the eye, and the water would be coming in right there. And then you get into small little residential or even like commercial, but small cartridge style pumps. But the same thing, you see that little bump? It's built into the casting. And that's just saying, hey, this water's path has to go this way to get into that impeller, into the eye. ECM circulators, we'll spend a little more time on this technology. I'll call it new, but it's been around here probably 10 years plus now. And it's been in Europe for a long time and came over. But ECM, electronically commutated magnetic motor. So a little different technology. We'll talk a little bit more about it. But the two main takeaways would be they actually have magnets on the rotor. So there's already a magnetic field developed, or a potential. And then they have a PCB, they have a printed circuit board. They have a microprocessor. It's a smart pump. That's kind of a slang term. You have smart pumps out in the industry. And they have microprocessors. So now you have software. Now you can make all kinds of decisions and make all kinds of modes of operation. How do I want to apply this pump? And this application might be different than, so you have a pump that can do a lot of different things, and you just tell it, you set it up. So that's become very, very popular. And we'll talk a bit about that later on in the next couple of weeks. But it's a very popular area. Just again, a couple of quick pictures of some of these single suction impellers. So that coupled inline pump, when they say coupled, they're using a coupler. That's what this picture is showing right here. Is I got the shaft of the motor through the bearings connected to the impeller. So there's a coupler that's connecting the impeller to the motor. So a coupled pump, horizontal inline. And all that means it's inline piping, right? Piping is inline, and then the motor sits horizontally. Nothing special. All different styles. Vertical, again, just the higher capacities. Split coupled, so you're getting into some really big vertical inline pumps, they'll call it. And then you get into end suction pumps. Now you're getting into more higher capacities. And the main thing being here, here's my inlet, there's my discharge off the top. I'm sitting on a base. I've got a coupler assembly, I got a coupler assembly, got a bearing assembly, and I have a motor sitting on this frame on this base. That second picture I showed you was a picture of these out in the field. Another picture showing. So that's kind of a dressed up. That's a pretty good, that's what you're going to see. That's what you're going to specify. You got flex connectors. So you got a suction diffuser. You got the pump, some type of maybe vibration or a transition fitting from the discharge to whatever size system piping, another flex. Then they have what they call a triple duty valve or a balancing check valve, service valve. That's the workhorse of the industry right there. A smaller version, 1531's close coupled, but it still has a little frame, a little base that it would sit on. The thing that's missing is it doesn't have that coupler, doesn't have that bearing. It's the motor shaft is connected directly to the impeller. That's just kind of a cutaway of it. And that'd be a cutaway of that 1510. They're just talking about the coupler. So anyways, and a coupler of that vertical inline. So the coupler has a couple of functions. Just be aware of it. I mean, it's all pumps, right? All pumps that have couplers. Transmit power from the motor shaft to the pump. So that's the connection. Flexible couplers will compensate for misalignments, just a little bit of a misalignment. It will compensate to connect the motor to that. I mean, you don't want it crazy because now it's out of alignment and you got problems with your bearings and all of that. Service department would be trying to prevent that. And then the other thing would be the flexible couplers can act like a fuse, meaning whatever reason, the motor's bound up, or more importantly, on the water end, if something got stuck inside that volute and that impeller's going to spin and it can't, and that motor's doing its job, he's got 25 horsepower, whatever it is, and he's going to spin, and this thing can't, well, instead of burning out the motor, the coupler will snap. It'll give. So it's protecting the motor, so it doesn't damage the motor. Of course, you want to find out why it snapped. So you inspect, maybe take apart, open up, see what's going on. But that's what they refer to as acting as a fuse, is that will break, that intentionally break to protect the more expensive parts of that pump or pumps. Real quickly, you're going to get some accessories. I touched on it quickly, but that'd be a pretty standard picture showing a return pipe coming down from a return riser into the inlet, the end suction side of that pump, and then off the discharge, I have this valve, very, very common, a triple duty valve. A triple meaning it can perform 3 functions. So the first thing we'll look at, that suction diffuser. Why suction diffusers? Suction diffuser, it's just its name. Before they were invented, when pumps went out in the field, like these base mounted pumps, as the industry grew and got bigger and bigger loads, inline pumps didn't work, they were putting these guys in. And what was happening is if you took this valve right here and you installed it close, like floor space saving, you're bringing that return, boom, bring it right into the pump. It makes sense economically, space. But the velocity of the water is different. The plane changes at the elbow will create non-uniform flow at the pump impeller. So now you got this impeller sitting there, and behind it is, it's a coupler, and it's got its a connection to the motor, and it's spinning at 1750 RPMs or whatever, and you hit it unevenly, and you torque it. And all of a sudden you can start wearing down on your bearings and, performance issues and all of that. And so they realized what was going on, and they did some testing, all the pump manufacturers, and the Hydraulics Institute talks about it and promoted it. And they said, hey, once you make that plane change, make sure you provide at least 5 pipe diameters, 5 times the pipe diameter of straight run. And all you're trying to do is that plane, that velocity, that non-uniform flow settles out. So now when you hit that impeller, you hit it evenly. So now it's not out of balance. It's not loaded on one side. So it wasn't until actually back to our friend I mentioned earlier, Gil Carlson, he had his hands on patenting a suction diffuser. And so what it did is when you think about mechanical rooms and space, you have, little drawing here up on the board, but make it 10-inch pipe or make it, 16-inch pipe or whatever the case may be. And you've got, you're eating up a lot of floor space just to keep the straight run of pipe. So he comes up with these suction diffusers X number of years ago. And this is just kind of an exploded view. They've got some strainers in there to try to collect any sediment that might be in the system, trying to protect the pump. but most importantly, let me see that. Nothing in the picture. They don't. Okay. They'll have these veins inside. There you go. There's a good picture right there. These veins sit right inside. So when that water takes that turn, changes direction, those veins kind of offset so that flow rate is now evenly loading the eye of the impeller. That's all it does. So it's an elbow, kind of a engineered fancy elbow, but it's very, very common. You see them all the time in your pump specs, especially the base mounted. It's floor space saving. On the discharge side, you'll see these triple duty valves, and they can act like a service valve. So service valve, what's a service valve? I got to service the pump. I'm a technician. I got to go out and work on the pump. I got to isolate the pump from the system. I don't want to drain the whole building down. So I'll isolate. So this triple duty valve, one of its functions, it can perform as a service valve. The other thing would be it's a check valve. You say, well, why would I have a check? I don't want reverse flow. So if I had two pumps standing next to each other in parallel, maybe one's operational, one's standby. I just don't want that pump discharge coming back down off this off pump. So I'm going to put checks in each pump. So this guy will perform that function. And then the last thing is it can act like a balance valve. And it's got a gauge, if you will, a meter that we can kind of throttle down on these valves. Got a better picture of it in a second. And it's kind of showing where I can create some pressure drop and I'm balancing them. So what happens is, and where it would be applied, it's not as common now as they're getting better with the sizing, and then the variable speed applications are kind of compensating with an over pumping pump. But if the pump is too big, and what I mean by too big is it can move more GPM than the system actually needs. It got designed for the right flow, but system conditions when things got installed were a little different, and all of a sudden it's pumping more than it needs to. It's consuming more energy, can create some velocity issues. So one of the quick things they'll do is they'll take this valve and they'll throttle down. And when they're throttling down, they're adding pressure drop. So now the pump sees all this extra pressure drop and he backs up on the curve. So he's not pumping too much. There are other ways to get there, but that's a very quick, fairly common over the years. So that's why they call it the triple duty: service valve, check valve, balance valve. You see them a lot. You'll come across them. Flexible connectors, and just like they described, they're just flexible, coming on the suction side of the pump. They're coming on the discharge side of the pump. It's just a way of connecting, offsetting any kind of discrepancies, if you will, alignments a little bit. They'll cover some sins. These are just some typical details. Your firms that you're working at probably already have these all on, file that you'd reference. But the difference would be just kind of recapping: end suction, base mounted, some of the details there. You got a base that needs to be grouted, needs to be nice and solid and not vibrating. And that vibration would then carry through the piping. And all of a sudden you're at Mass General in your operating room and you're unacceptable. All that, how that all gets installed, how it gets detailed. Inline pumps, they're going to say, hey, we had to put the brackets on the piping that's holding the pump, that's in between all these little details. If it's a really large inline vertical pump, they might even the manufacturer might provide a foot pedals, or a pedestal, I should say, to take the weight And then again, just another inline there. So those are just some of the common details you might see. Double suction, getting into that larger VSX we talked about earlier. Well, that's trying to show us is now as the flow rate gets really big, relatively speaking, and you try to use that end suction pump, you got so much load, so much thrust, so much bearing torque, if you will, on that. You can really, wear and tear the bearings, the seal of that pump assembly. So what they'll do is, again, look at that kind of a cartoon drawing up, but what they're showing is the water splits and it loads the double suction impeller. So now, instead of having everything coming just one way, it comes equally and it balances. So that load is gone. They cancel each other out. So it takes a lot of wear and tear up the bearing assemblies and all of that, just serviceability, life of the pump tremendously extended. That's why it's become, when you get into these large chiller plants and large flow rates, when I say large, thousands and thousands of gallons a minute, very common to see this style pump, some version thereof out there. So they're showing like the impeller. So here's your two eyes right there. There's a picture of it. If you're taking that impeller and just turned it a little bit, there's a picture of one, you'd have the exact opposite on the other side. So very, very common, these VSX HSCs.
So George, there was a question on here. So it was, Sam Appleman was asking if there's a PVC suction diffuser. I've never come across one, but I can't imagine. He was asking if there was
what was the
a
material?
PVC.
Oh, I have no.
I've never seen one, but we don't do a ton of work with PVC.
Yeah, I don't know if that'd be process or pool or something.
What was it?
In the lab,
They,
in the
they,
chemical labs, they have.
you'll see some PVC suction diffusers. I gave it I was searching it a bit online. I'll give it another look, but I can't imagine why there wouldn't be the basic item.
I haven't seen it personally. Doesn't mean anything. This VSC. Willie, are you still live? Okay. The VSC, the original intent, and this is X number of years ago, was it would have been a more of a horizontal in and out, whichever direction. And they just come up with this and they said, hey, if we can do this VSC and have the vertical and the vertical suction and discharge just from a floor space saving, again, just chasing after minimizing the real estate that they were eating up in the mechanical rooms. It a lot of times played a favor with the engineer and community to just save some floor space. So that became very popular. A couple of pictures from a pretty good size application in a mechanical room, and they're just kind of lined up, whatever it looks like, maybe 3 or 6 or 8 of them. So you're dealing with a serious mechanical space there. You wouldn't use a suction diffuser there. Correct. Meaning we wouldn't need it. Is that what you're getting at?
No.
We would? Well, yeah. Yeah, I think that was all, well, I'm sure that was all engineered in the design to evenly load that suction, double suction impeller. And it's a good question, Sino. But we'll, I believe just because of that design, the need for that is not needed, not used, and never experienced a problem. I've seen it where they've, let me see here, where if they don't handle this properly before it gets to, so depending upon how it's installed, what they're referring to here, that even though I have this double suction, if I don't pipe it properly to the inlet, depending upon the orientation, the vertical a little different, but they were concerned about distance and straight run. But when you're talking that vertical and it comes right in and splits them evenly on that impeller, but they do show, and this is right out of the installation manual of the pump. If you're piping in this orientation, don't do that. So horizontal left to right, horizontal to the pump shaft. So there's different details, you got to be aware of. But what we were just kind of looking at is, maybe more of that vertical to vertical, but you get into some of that horizontal or horizontal to vertical. So the point of all of that is just you all the different style pumps you guys are going to be specifying and selecting and all of that. And there's a reason why there's different designs. They just didn't settle on one, say, hey, this widget fits all applications. It's kind of a broad range. It's not too broad, but it's broad. And you just want to be aware of where and why. And again, details that your firms, I'm sure, already have of how to handle these double suction pumps, or these double suction impeller pumps. Sometimes a question will come up. That's actually, before I get there, just a good picture of showing there's the splitter right there. So that water is coming in here and splitting and entering into that impeller that's sitting right here. And then the discharge is coming out the top here. So that's, engineered and built into the molding, the casting of that volute end of the pump. But sometimes someone will say, hey, when do I go to that expense? Like, when do I go here versus why can't I just stay with this? Kind of a little more traditional and pretty popular, very popular, actually. And there are different reasons, and different firms might have different philosophies, but as a general statement, typically flow rates where they're consistently going to be above 1,500, maybe up to 2,000 gallons a minute or more, you're probably going to jump in this direction. You're going to find plenty of pumps that can get into that range and higher. It's just it's the serviceability down the road. What kind of beating is that pump going to take versus this is like, bring it. I'm built for this. I'm made to do this. I can do it. You're just going to be babysitting me quite a bit over the next 10, 15, 20 years in the mechanical room versus a pump. You stay on top of the bearing, stay on top of the greasing and all of that. The annual stuff survives, thrives in that environment. So it's sometimes a little more, not sometimes, it is more money up front. But if you're looking at it from a client perspective and serviceability, and the building's going to be here for the next 50 years, 30, whatever those things that influence your decision making, so that's just it's not written in stone. You don't have to live and die by it, but it's a fairly standard number that gets passed around from engineers to engineers. Yeah, for all the inherent, design characteristics, of course, comes with that a different price tag. So sometimes if they're just looking at price, they might get steered in a different direction, but then they might be paying for it after the fact. That's all. So be aware. So less expensive, a little easier to maintain that single suction. The double suction eliminates axial forces on the impeller, certainly a longer pump life and capable of higher flows than that single suction impeller. Just I guess you call it a guidance, if you will, on pump selection. Again, nothing written in stone. But flow rates, what style pumps, inline 50 to 150, 50 to 200. And again, we're going to give you this presentation in a PDF form, so you'll have all of this to reference. But getting into the larger flows, 1,000, 1,500, you get your base mounted pumps up to about 1,500. Then you got your double suction. You get bigger than that, your VSCs, your VSXs. Again, more of a, I guess the right word is guidance. Right. Just moving from pumps real quickly over to air separators. Just as far as different hydronic components you're going to see in the industry or see out there. Just a quick little paragraph, if you will, out of ASHRAE Systems and Equipment Handbook, but obviously it's just saying air and other gases are not eliminated. They can cause air binding in terminal units, which can affect heat transfer, corrosion, noise from a client's perspective, someone living there listening to gurgling going through the piping. That's not necessarily a nice feature. And then from a pumping standpoint, just reduce pumping capacity and loss of hydraulic stability. You got a slug of air come into a pump that's spinning at 1750 RPMs, and it's it's the load of the water, and all of a sudden there's this collection of air. It can deload and it overspins, and then another slug of solid water comes in, and that's sometimes, if it's serious enough, you'll start snapping couplers or pump shafts, and so things to be aware of. So the point being that we just want to make sure air is not an issue in a hydronic system. So where does it come from? So one of the manuals you have there, which again, don't reference it, but it is there, this air management. They have right from the very beginning, this, it's kind of a silly little picture of a, standard glass of water in a, say, a home, and they fill it with water out of tap water and fill the glass. And then just put it on the counter. And the X number of hours later, come back, and all these air bubbles come out of the water that when you first filled it, it was like crystal clear. Like, where'd the air come from? Well, you change the pressure and you change the temperature. Wasn't aggressive, it's just ambient, maybe going from 45, 50 degree street water to 65, 70, But the point being H2O, there is an element of oxygen in water. And when you heat it or you drop the pressure, the water can't hold as much air in solution, so it comes out, and it comes out in the form of bubbles, air bubbles. So then there's different technologies, if you will, that are used in the industry to get rid of the air in these commercial settings. These first guys, you're not going to see them. Very, very rarely. This is residential, but you will see coalescing and you will see centrifugal. Those are the two that you're going to see commercially for the most part. And this would have been more original, still very, very popular and very effective. That coalescing has become popular over the years, a little more expensive, but also maybe you could say a little more efficient at catching air bubbles. But there's different technologies. And so what they're trying to say here is with velocity, whether it's a little, 2-inch diameter pipe or a 3 or 4-inch diameter, whatever the case may be, the point of velocity is if you can slow the flow rate. So standard industry standards would be around 4 to 5 feet per second water's moving in the system. So if you have water coming out of your boiler plant, the heat source, and it's got some air bubbles that have been released and they're flowing along with the water and they're moving at that velocity, and all of a sudden you enter into this larger diameter area, this low velocity, the water slows down to like a 1/2 foot per second. Mother Nature takes over, the bubbles will be buoyant and they'd float, and you'd vent them either up to a compression tank or more commonly through a vent. You get into coalescing, and it's there's a coalescing medium. Typically, it's stainless steel surface with some fingers or brush, almost finger-like brushes. What you're doing is you're just giving these little bubbles all of the surface area to gather, to collect. and it creates the surface tension, and they kind of stick as they go flowing through. But sometimes those bubbles, they'll call them micro bubbles, are fairly small in and of themselves, so they're not that buoyant. But you're given enough of these small ones and they gather together, they become a larger bubble, and they then are buoyant, and they will vent out through your high capacity vent to the top of the device. So it's just a more efficient method of collecting, separating air from the system water as it's leaving the boiler plant. That would be what you'd see commercially on a commercial grade. They, get up to some pretty good sizes, big sizes. I think they're showing here all the way down to what, 24-inch, I guess. So 2-inch to 24. So you get some pretty big capacity or potential capacity. But coalescing, or CRS, coalescing removal separator. And then the last one is that centrifugal action that we call ours a roll air troll. Doesn't really matter, but it's based on centrifugal action. And what they're trying to show, and they'll use the word tangential, is when you look at it horizontally at this air separator, you got an inlet on the top right and an outlet on the bottom left. You're like, okay, big deal. And then when you look at it from a plane view or a bird's eye view, they're on the same side. So as they come in, and that centrifugal action causes them to spin to get down to that outlet, the heavier water, right, gets flung around the outer shell of that centrifugal air separator, and the lighter air bubbles gather in the middle. And that's what they're trying to show here through this, like almost like a computational computer drawing. This heavier water gets flung to the outer edges of the shell, and the air gathers inside. There's like a collecting tube. Oops, wrong way. And that's what they'll show is in the middle of this drawing right here is this collecting tube that'll gather this air and direct it and get it out of the air separator. Very common, very efficient, been around a long time. And they have them tested, and they have the efficiencies and first pass, second pass. And just know that they do a good job, whether using the coalescing or using centrifugal. And those are both very common commercially. One last thing just that you might bump up against, you might hear from either from us or a boiler manufacturer selling multiple boilers and saying, hey, I've got this low loss header, or I have this primary secondary header. It's just another technology that's become popular, especially with the multiple boiler applications that are taking place out in the field. And in addition to acting as a primary secondary connection, they have also been, they've become the air separator between the boiler plant and then your distribution pumps and system and what's going out to the building. They'll use this low loss header to vent air. The primary principle behind it is back to that low velocity. And this little cutaway drawing does a good job. And what I just want to show you real quickly is, depending upon the size of the low loss header, in this case, they're showing a 2-inch pipe connection. So 4 connections, a boiler in, a boiler return, a system supply, and a system return. And the point being that at that 2-inch pipe, you got a certain flow rate that you probably don't want to connect it to anything greater than. So in this case here, they're showing a quick example of about 40 gallons a minute on 2-inch pipe. But then what they do is they engineer this middle part, this diameter, such that that velocity drops from 4 feet per second to less than half a foot per second in that area. So again, back to velocity, heated water, bubbles come out of solution, they're coming along with the pumped flow, and they enter into this, and they get vented. So the manufacturer says, hey, in addition to being primary, secondary connections, let's put a high capacity vent on top of these things, and we can use it as an air separator. So they do. So it's common, not big commercial, maybe light commercial. You'll see these a fair amount. Bigger stuff, you're going to see that coalescing, and you're going to see that centrifugal. Those will be the two main. But this has become, it's probably the latest on the market in the last 10 years or so. General statement, where do you put them? The hotter the water, the less air it can hold. The cooler the water, the more air. The lower the pressure, the less air, and the higher the pressure, the more air. So ideally, you're trying to chase after where's the water the hottest and the pressure the lowest, relatively speaking. And that's where you want. When possible, select a point which will have both the highest temperature, lowest pressure. When this is impossible, the point of highest temperature should receive first consideration. Except for potentially when you're getting into some high-rise buildings, you might have a couple different locations. But the hotter the water, air comes out. So typically that's why you're always going to see in your boiler plan or your drawings that you have back at your firm's office, out of that boiler or boilers, probably that's where they're locating that air separator. That's the reason. The water's the hottest, the air come out. Because typically the other thing that's happening is what's on the other side of that air separator, all the things we just talked about, all the pumps. Well, the last thing we want to do is put this slug of air right into the suction of that 100 horsepower motor and then deload it and then reload it and then snap the impeller, or the shaft or the coupler or etc. So in addition to collecting the air and not letting it get it out, we want to protect the pumps. Yes, sir. Meaning this one right here?
Yeah.
Well, typically, if you just put it in line, yeah. You just need the full, well, yeah, what are you saying? What are we doing? Straight through, pass through? Yeah, it's a light spot in the river. I'm missing what you're asking. Like if you wouldn't put this in, I guess you could, you just, the point behind it, why you would buy this normally would be, I got a boiler plant, 1 or 2, 3 boilers, primary, secondary, they have their own pumps. So instead of putting a set of primary, secondary tees, like Gil would have talked about years ago, this is like kind of a pre-made primary, secondary connection. Yeah. You normally wouldn't. Yeah, that's the application. Yeah, the 2 ports, you're just going through it. Yeah, right. Technically, would it separate air? It would, you just wouldn't go buy it. Normally, you wouldn't go buy that, the 4 port. Yeah, right, exactly. Right. But moving along here, just expansion tanks. So another component you're going to see, you guys are going to be tasked with sizing expansion tanks. And one of the fourth week we get into is separation and expansion tanks in a greater detail. But, old technology, I'll show you a picture of it later on maybe. And it's the last time you'll probably ever see it in your career. But years and years ago, that was the standard tank that they used. And then as technology came and butyl diaphragm became a form of using for expansion tanks, bladder tanks, diaphragm tanks, the industry quickly moved away from the older style. They called it a compression or a standard tank, a standard compression. The main difference between the top picture and these 2 lower ones, there's no bladder up there. It didn't exist. So the air and the water touched. And you dot your I's, cross your T's, you can make it work, but it was pretty finicky. As soon as these bladders are developed and applied to expansion tanks, and now you could separate system water on one side, the gas, the air on the other, pre-charged. Same thing on this bladder style. Air in the shell, water in this bag, this bladder bag. A lot of those finicky go away. A lot more friendly, easy to install, easy to service. So the industry absolutely went this way and has been for a long time. So these are the 2 you're going to come across. Someone going to say something? No. Okay. Old school, like just for old original expansion tanks would have been old, like late 1800s, early 1900s, but gravity hot water, you still heat water, it expands, right? You heat water, it expands. It's got to go somewhere. Water's not compressible. So you fill a system with water and then you heat it, it expands. It's either going to blow apart, it's going to blow a relief valve, it's going to create, you got to have a place to go. So they addressed that with these old gravity. They'd put a tank, an open expansion tank, up typically in the highest point, which would usually be the attic of a large home. And you'd have these old tanks. And I've been up in homes like old, 100, 120-year-old, 150-year-old homes, and they'll be up there, disconnected. They've already moved on and all that. But the guy said, I'm not taking the time to lug this thing out of here. But that would have been an open expansion tank. And the water, as it heated, it would expand slowly and it would rise up into, and you could watch it on the gauge and you'd see, what was going on. And then, so it wouldn't overpressurize, it was vented. And typically they just have the piping penetrate through the roof. It's very simple, very subtle, but that was kind of your first expansion tank, so to speak. So why do we need them? Maintain pressure. We'll get into this in more detail, but maintain pressure within acceptable bands. So when you think about it, when you first fill in a system, say we're talking hydronics for a moment, heating for a moment, down in the basement, and that's where the mechanical room is, you got boilers. Boilers have relief valves. So I have this initial static weight of water sitting on top of the boiler, on top of the diaphragm of that relief valve. And I'm going to fill the system up. And so at the beginning, when it's cold, I've got this pressure. So maintain a certain acceptable band. Well, the beginning part is your fill pressure. And then when I go to heat it, there's thermal expansion. So as that water gets heated and the molecules expand, they go somewhere. Well, the tank's job is to absorb, and it does. The key to what your role is, make sure that tank is the right size. So when that pressure or when that water expands and it moves into that tank is the right size. So as that water comes in and it squeezes the air and the pressure climbs, it never gets to my relief valves. I don't want my relief valves opening and closing. I want them closed. I don't want them active. I don't want to be dumping out water out of a closed system, because then I bring in cold makeup water that has a ton of oxygen. Not good. So I want to keep the acceptable band is fill pressure at the beginning, relief valve, heat the water, pressure starts to rise, relief valve stays closed. It's a big, it kind of sits off to the corner of our expansion, but it does do a pretty good, pretty important job to the integrity of the system. So just a kind of a visual, if you will. Take 2,000 gallons of water at 40 degrees, heat it to 180. The expansion would be an additional 56 gallons. I get that. It has to go somewhere. And if it doesn't, it will on its own and open up relief valves or, whatever, even worse. So that's the job, because water in these closed systems, you can't squeeze it. It's not a gas. Water's not a gas. It's a liquid. It's not compressible. So I got to find a place to put it. So that's, great picture. Picture speaks 1,000 words. Just real quickly, old picture or old application, we had saw a steel tank. They called it air control. Air and water sat on top of each other, right? They saw each other. There was no bladder, no diaphragm, no butyl. So any air that got separated, they controlled it and they sent it to the tank. They never vented it out. That was the principle behind that old system, just for history standpoint. But here, oddly enough, had a job a couple of years ago now. Engineer spec high efficiency condensing gas, natural gas boilers, probably a couple 8, $1.6 million, decent sized apartment building, whatever. And he specified a steel tank. And he was just that was how he was schooled as an older engineer. That's what he knew. So we did it. So I just got a kick out of it. Here I got this brand new technology using it with this older technology, but whatever. It works if it's done right. It's just very rare. It's always going to be this air elimination. I already have my source of air in my bladder expansion tank. I don't need any more. Anything that I separate, get rid of it. Air elimination. Any air I find, vent it out of the system. I don't want to bring it back. I don't need to. I've already got it. So that's what we're going to see. And again, they might call them pressurized tanks, but a bladder style and a diaphragm style. The bladder truly is a bladder. And it's, when the when the tank is empty, I mean, it's not filled with system water, the air that's in this shell kind of takes that bladder and squeezes it. So it's just real compact along this dip tube that feeds the system water into the bladder, and it compresses. As you turn those boilers on, those heat exchangers, whatever the heat source is, and the water starts to expand, it's going into this tapping, the system connection, and it starts to fill. And as it's doing that, what's happening to the volume of air? It's getting squeezed, it's getting smaller, pressure's rising. And the whole function is, okay, as long as we sized it right, the pressure will rise, but stay well below my relief valve settings. Everything's good. A bladder, excuse me, a diaphragm style, a little different. They're going to have, it's usually like, this is referred to sometimes as a full acceptance. Whatever the tank volume is, that's the volume of water that that tank can absorb. These are partial acceptance. And so there's a total tank volume, but then there's how much water can I actually let into this tank. We'll get into that in that fourth week. We get into this in greater detail. But diaphragm and bladder. Smaller systems, probably going to see diaphragm. A little bit larger and larger, that's when you're going to see a lot of bladder style tanks. That's pretty common in the engineering community. We'll talk about that later on pre-charge. Just a visual, one of the comments that kind of alludes sometimes out in the field, the service technicians and the installers, is the way these tanks and the way you're going to size them and the way the software that the tank manufacturers will provide to you to size them is there really technically should be no water in the tank when it's connected to the system and the system's cold. You haven't fired the boiler plant. So the pre-charge, the air cushion charge, technically, depending upon where the tank is, a lot of times it's in the mechanical right next to the heat source. It's all down in that mechanical space. So that will get pre-charged to the same setting as the fill pressure to get the water to the high point. So if it takes 20 pounds to get it to the high point, I want to make sure I have air charge of 20 pounds so that when I connect it to that system and it's 20 pounds sitting here, they balance each other. If I kept the tank at, say, 12 pounds, connected it to 20, as soon as it connected, naturally that 20 is greater than 12, water's going to go into the tank. And that's when the tank's cold, when the system's cold. Now you turn the boilers on. Now that water really expands and there's no room left at the end and the relief valve blows. So we got to be aware of that. Fill valve settings and pre-charge all work together. Just a couple of cutaways of the tank, different style. Another component real quick, we're getting close, we can break for a quick bite to eat. Relief valves, pressure reducing valves. And just like the term PRV, you'll hear them sometimes out in the field, they'll be called fill valves. But PRVs is a pretty standard term. And all its function is to take whatever incoming pressure we have on the street, and then typically it's knocking it down to whatever that particular building I'm working on needs to fill the water to the highest point. So what is the setting? It's a function of the height, the static height of that system. Meaning a 3-story, a 4-story, a 5-story, all three of them are going to have different settings because they're different heights. So my job down here in that basement is to make sure I have water at that highest point. Right? It's got to be there. The pump's job, when the pump turns on, he's not lifting water in a closed system. He's circulating. The water's already there. All we want to do is circulate heated water or chilled water through that building. So here's a quick number, and we'll get into it again a little bit later on, but divide the number of feet from the fill valve location to the highest point in the system by 2.31. And that becomes your pre-charge setting. And what you want to do to that number is add 4 pounds. So at the very top of that building, we've got 4 pounds of positive pressure. If I figured out what that dimension was and I set it and I got water there and I didn't add any additional, what would the pressure of the water be at the very high point of that system? 0, right? Now, if I had, say, a float vent, it's not uncommon on these high top of the systems to put a air vent in case there's any air bubbles, they might get rid of the air. Well, if I have a float vent up there and it's 0 pound system pressure that is attached to, what's the pressure on the other side of that vent? 0, right? Atmospheric pressure, so 0 pounds gauge. So there's no motive force. So the industry standard learned that. They said, hey, whatever it takes to get to the high point, add around 4 to 5 pounds positive. So now I have 5 pounds here. I got a vent. I got 0. I have a motive force to drive any air bubbles through that vent and get rid of it. That's its only purpose. But whatever that number is becomes very important to that expansion tank's pre-charge. And where to locate them, typically somewhere close to the expansion tank. If I can put that fill valve somewhere near, in this case here, they're showing commercially, my bladder tank ties in right here after my air separator before the suction of my pump. That's all positive. And what's right beside it? My fill valve, my pressure reducing valve. So that's all pretty good. Relief valves, very important, very quiet, hopefully not active at all, meaning they're not discharging. If they do discharge, hopefully, they're doing their job, but why did it happen? But they're sized on 2 functions, because a relief valve typically is pressure. What's the equipment, the boiler, the heat exchanger, whatever it is, the chiller? What's the maximum operating pressure that component can see? And the manufacturer tells us, they know what it is. But then, especially if it's a heat source, how many BTUs can it develop? Because if that relief valve does open because he's seeing too much pressure for whatever reason, and the boiler's firing, that relief valve says, hey, I got to unload this pressure so that I don't explode or I don't crack or I don't break. I also have to be able to handle how many BTUs that heat source can develop. Because if I have a relief valve that can open up under the right pressure, say 75 pounds, and I can unload 1 million BTUs, and I got a 5 million BTU boiler that's firing, well, that 5 million is creating more than what the 1 million can get out of that system. Pressure is going to continue to rise. So when you look at relief valves, pressure and BTU capacity, it's got to exceed. Can't exceed the pressure relief of the manufacturer, but it's got to have the BTU discharge capabilities. Let's stop and eat. Let's stretch our legs. Everybody that's listening in remotely, we're going to take 5:25. We'll be back at say 20 of, quarter of at the latest of 6, 20 of 6. All right. Okay, perfect. For everyone remote, we're going to get going here a little bit after 20 of. I apologize for that, but we're going to jump into it. As the screen should show on your computer, understanding pump curves and system curves. Kind of the next topic, so to speak. Having to do, we talked about pumps and all that. Okay, well, what do they do? And how do they do it? And how do you, without taking a huge dive, but what's involved with selecting pumps? And when you look at pump curves, what are they telling us? So whether it's on a laptop or a printout, software, or whatever the case may be. So just starting real basic, developing a curve, generally speaking, keep it simple, but on the horizontal, left to right, that bottom graph, that bottom line, that's going to indicate it's typically where they're going to show the flow rate and capacity. So gallons per minute, pounds per hour, typically gallons per minute. And on that vertical axis on the left-hand side would be the feet of head that the pump can develop. And we'll talk about what that means. So there's kind of 2 conditions. What's the BTU load? What am I trying to move for flow? And then as I do that in the particular system I've designed, what's the resistance? What's the pressure drop of that flow moving at the right size with the right size pipe and all of that? So I got to overcome that energy, that resistance to flow. So this pump curve will it's like the DNA saying, hey, this pump can do this many GPM, it can overcome this resistance. Will it work? Is this what I need, etc.? I mean, very simplified, but that's a general statement. So just getting into establishing the flow, again, back to a couple little pictures here, but in a pipe, we got water moving. What's the flow rate? Things that we want to be aware of. Temperature change of the system fluid, the delta T. right? What's the change in temperature? In a hydronic heating system, it's always going to be a temperature drop. Obviously, we're getting rid of energy. We're getting rid of BTUs. So we leave the plant at X, we take a temperature drop, and we come back cooler. And that cooler drop is the energy that we transferred upstairs. If it's chilled water, just the opposite. It's going to leave the chiller plant at 40, 42, 45 and come back warmer because the heat that was in the space, we're taking it away. So it cools down and maybe dehumidifies a little bit. Specific heat of the fluid, generally speaking, not always, but generally speaking, specific heat of 1, water. You get into glycol, it changes a little bit. You got to be aware of that, both flow rate and pressure drop. But a lot of the examples probably will reference water as 1. And then just what's the load? What's the amount of heat or heat rejection required, the BTUs per hour? So a simplified little, maybe a fan coil. So I got a supply, hot water, red indicating hot water entering into that fan coil. I got a fan behind it, blowing's coming back, or leaving, exiting cooler, red to blue, real simple. So what's the supply temp? What's the return? The delta T is the difference. Simple, easy. Average the two. If you're looking for what's the average water temperature, might get into the capacity of that heat exchanger or that heat transfer of that coil. Let's make sure. Yeah, Willie said he can hear me. So let me see if this. Yeah. I want to do that. Can I just move that up? No, thank you. So anyways, just how much heat is the water carrying? The mass flow rate. So BTUs per hour, you start to build a formula of how to calculate GPM. So pounds in an hour, 1 BTU per pound in Fahrenheit, delta T. Kind of expand it. A pound of water, or how many pounds? So a gallon of water is 8.34, 8.33. We can argue what's the temperature and all of that, but pretty safe number, 8.34 pounds per gallon. How many minutes in an hour? BTUs per hour, flow rate in gallons per minute, 60 minutes in an hour. Talking water, 1 BTU per pound, delta T. You start to cancel out some of these factors, and what you're left with is you take an 8.34 times 60 times the delta T if you're dealing with water. You get into a glycol or whatever, you get a little different density. The factors will change a little bit, but still it's pretty close. The point being that 500 is the weight of a gallon of water, 8.34 pounds times 60 minutes in an hour, times the flow rate, times the change in temperature. What's a BTU? It's a simple statement. And you guys learned it probably first class of engineering, right? Yeah. So yeah, I didn't learn the joules. I learned the BTUs, but yeah. But British thermal unit, right? So you know when it was developed? 200 years ago, 1824. Gentleman named Thomas Tredgold over in England. He was the first engineer, scientist / engineer / inventor that wrote a book on heating. And he designed the House of Commons over in London, the ventilation system, and all. He designed that 200 years ago, give or take. So anyways, he's sitting wherever in his office, in his laboratory, and he had basically a pint of water with like a flame, a Bunsen burner, some version thereof, with a Gabriel Fahrenheit thermometer in it. The water was 62, and he heats it to 63. That's it. Took one, and the pint turned out to be about a pound of water. So he took 1 pound of water and he heated it 1 degree. And he said, up until that point, there really was no expression to describe what he just did. So he said, I want to describe that. He's into heating. He's an engineer. He's a scientist. Being from London, being from England, calls it a British thermal unit. 1 pound of water, 1 degree Fahrenheit. So when we keep talking about delta T's and 20-degree drop here and a 10-degree rise on chilled, that's that change. The pounds, how many gallons, how many pounds per gallon, it all kind of just math, all comes together. But it's an easy number to work on. 500 times GPM times delta T gets you BTUs. Or you kind of go the other way because you multiply the 20-degree, which again, not locked into. We'll get into all kinds of examples where that changes on the heating side. Chilled water, industry standards, nothing again is ever written in stone, but 8-degree, 10-degree, 12-degree rise. Those are kind of the three ranges within the chilled water world where it's leaving at 42, coming back at 52, leaving at 42, coming back at 50, leaving at 42, coming back at 54, 8, 10, or 12-degree temperature rise. On the heating, 20 is a very safe, but like I said, we'll get into examples where that changes. But when you do the math, it's 10,000 times GPM equals BTUs. Or go the other way. BTUs divided by 10,000, there's your flow. Simple. So anyways, so when you're talking about a pump, you need to know the flow rate. So what's the load? 1 million BTUs, 100 gallons a minute. Added 20-degree delta T, whatever. And you can play with different delta T's. It's not locked in stone. 25 is going to influence 30-degree, 40-degree. We get into primary, secondary, and we have some pretty aggressive delta T's. That's okay, because all you're trying to do is move energy, move heat. And so anyways, simple, easy. Pump head. So just some terms. You probably, again, studied all of this or learned all of this, through your college career, but pressure, a force applied against a unit of area, pounds per square inch. Total mechanical energy, so fluid head contained in a pound of fluid. Pump head, energy or work added by a pump as the fluid flows through the pump. So I'm coming in that suction, that impeller spinning. Why? Because I got this motor that's consuming energy, adding velocity. I'm adding energy. I'm adding work to that water as it flows through. Hydronic system, this with liquid flow and 3 factors influence how mechanical energy head is in the fluid is transformed. So you get the force of the static pressure. You got the head due to elevation changes. We'll talk a little bit about that. Be more open systems, perhaps. And then the head due to the velocity of the liquid, which is it's the flow rubbing against the inside diameter of the heat exchanger, the boiler, the piping, etc. Kind of a weird drawing, and typically you're not going to see something like that. But what they're trying to show here is that the pump could develop a 3 psi differential. And we'll get into the reason why, but 3 pounds times 2.31 is the conversion. It would be 6.9 feet of pressure differential, feet of head that pump can develop. And what they're trying to show here is the water column elevation head equals the pump head. So he can't discharge past that point because he can't develop more than 6.9 feet ahead, and maybe that pipe happens to be 7 feet tall, or whatever. So it's open to so it's just showing that what that pump head is in an open, how that static height has a factor, plays a role, if you will. Because what they're showing here, pump running, but no flow. It's almost like it's deadheading. It's just sitting there churning, and it's holding this water column up, but it can't go any further. And if it can't go any further, I'm not displacing, I'm not bringing in any more in. I'm just sitting there spinning. I mean, again, it's a weird analogy, the picture, but it's just trying to show versus this. Now, this is what we're going to design around all the time. I shouldn't say all the time. A high percentage of your application is going to be this expression right here, closed loop. So in a closed loop system, friction loss only comes into play. Pressure, velocity, elevation are all equalized at all points. Friction head loss is the pump head. It gets asked all the time. Our inside sales staff over the years always gets this call where a call come in saying, hey, I need to buy a pump from you guys, or you need to help me size a pump. Ooh. That's not good. Do I not have it? Haha. It got unplugged. I'm glad they gave me the warning versus all of a sudden the class is dismissed. That'd be a big fail on the first night, huh? But anyways, so the pressure drop. Well, my point I was leading up to is downtown Boston. You're in Beacon Hill or Calm Marlboro, whatever. You got the brownstones, 5-story buildings. Inevitably, we'll get a call downstairs. I need a high head pump. And, you know, in contractor, he's out in the field and he's down in the basement. He's got to put a new pump in. I don't know the GPM. You can help me out with that, but I know I need to lift the water to the high point. It's just it's whatever it is. It makes sense in a way. Actually, you're down there, you turn the pump on, it's going to lift the water up. You know, the water's already there. That's the fill valve. That's the expansion tank's job. The water's there. We just want to overcome. This is an expression you might have not heard before, but a known pressure drops. So components, boilers, zone valves, control valves, heat exchangers, the manufacturers all list a chiller. They'll tell you what the pressure drop is at a certain flow rate. So we want to add those known component pressure drops plus the flow rate and the diameter of the pipe. And what's the length of run? What am I up against? What am I pumping against? So in this case here, what it's saying is, hey, in this scenario, if I was to have gauges on the suction and the discharge of the pump, and I saw a suction of 12, a discharge of 20, okay, that pump's developing 8 PSI. So I take that 8 PSI and convert it to feet of head times that 2.31, 18.5 feet, assuming, water as my medium. So that pump can develop 18.5 feet ahead, which will allow a certain GPM to flow through that closed loop system. Whether that's a 10-story building, take that 10-story building and lay it on its side, and it's that much longer 1-story. It doesn't matter. It's a closed system. It's just piping frictional resistance. Yeah. Just real quickly, just a little definitions or whatever, but when you're looking at gauges and the contractors, the mechanical contractors out in the field, and they're looking at gauges, pressure equals force area. So they're just trying to describe, if I had 1 pound weight sitting on a 1 square foot and I divide it 1 square foot, 144 square inches, I'm looking at 0.007. If I take 1 pound across 1 square inch, now I have 1 pound per square inch, the gauges. It's just a hell of a lot easier to read. So when you're looking at these gauges, is per square inch, pounds per square inch. That's all. So another thing just to be aware of, we got absolute pressure. Oops, a little too quick there. So we have absolute pressure, and we have atmospheric pressure, right? If we had gauge pressure, which is this next one right here, gauge pressure, it's measured above atmospheric pressure. So the gauge is starting at 0 pounds is atmospheric pressure. And then from there, I'm adding above atmospheric. If I was into vacuum, which hopefully in a hydronic system, you don't go into vacuum, but there are times when it could happen. But certainly if you're dealing with steam systems, you might be operating in a vacuum by design or other applications, whatever. But vacuum being obviously below atmospheric pressure. So it's just applying different numbers. And typically assuming elevation at sea level, atmospheric pressure, 14.7 PSIA. So if I had a gauge, it would be reading 0 pounds. And then if I had a static pressure or a fill pressure of 4 PSI, the gauge would be reading that 4 pounds. It's assuming it's already including the 14.7. So it's just being aware as you're looking at gauges out in the field and how to interpret that information. So static pressure, pressure caused by the weight of a column of fluid. So rule of thumb for water, 2.31 feet, again, equals 1 PSI. So if you were down in the basement and you were looking at, say, what does P1 represent? What they're saying here is, remember I talked to you guys real quickly right before break about the fill pressure that it takes, and then we added, say, that 4 pounds, that positive. Well, I might see that up at that gauge. I might be reading 4 pounds here. So what I'm reading down here would be P2, maybe that 4 plus whatever the feet in height, the height in feet, I should say, divided by 2.31 would be the total reading on that gauge. If for some reason you're on the 1, 2, 3rd floor and you're looking at a gauge here, he'd be reading the height between this floor, 4th floor, 5th floor, plus whatever that gauge. So again, just be aware of some of those, what those gauges are telling us, where are we in the system. Where does the 2.31 come from? 1 cubic foot of water weighs 62.4 pounds. 1 square foot area has 144 square inches. It's math. You guys were doing this back in school, I'm sure. But you're just going back and forth between feet of head, 2.31, or you're reading the gauge, 0.433 PSI per foot. The point being that, you have a column of water and it's 2.31 feet high. You would have that gauge sitting at that base, it'd be 1 PSI, 1 pound per square inch. And if we described the tube that the water was sitting in was 1 square inch, just again, a visual elevation, second form of fluid head. Pressure head, again, another little visual, but all we're saying here is as the water's flowing through the piping, there's frictional resistance. It's eating up the energy. We want to calculate what that energy head loss is when we select the pump. So a relationship that exists between flow and pressure drop and the change in flow and what the new pressure drop would be. So what we're talking here is I got a scenario, just a snapshot. I got a flow rate in a certain diameter pipe moving 3 gallons a minute. And from, call it P1 to P2, I'm experiencing a 5 pound pressure drop. Now, that's a couple hundred feet, a couple thousand feet, whatever it is, it doesn't matter. But in this scenario, with flow 3 gallons a minute flowing through this given set of conditions, it's causing a 5 pound pressure drop. So now this is where it starts to get into pump curves and system curves. And you say, hey, if it's 3 gallons a minute causes a 5 pound drop and I double the flow rate, I can mathematically calculate what's the new pressure drop. And it's based on this formula over here. And what we're saying is the change in flow, known flow, final flow. So the change in flow squared multiplied by your original design head or known head will become your final head. So wrap it all up. There's a squared relationship between the change in flow and the change in pressure drop, the corresponding pressure drop. So if you plug in these conditions, I know I'm moving 3 gallons a minute and I created a 5 pound pressure drop. I want to increase the flow rate for whatever reason. I want to double it. What's the pressure drop going to be? So the original was 3. The new one, Q2, is 6. 6 divided by 3 is 2. 2 squared is 4. 4 times my original pressure drop of 5 is 20 pounds. It's a squared relationship. It's a hell of a lot more. So, and where this, sometimes I'll share this with like some of the contractors in the room in a different seminar, different type of thing. Because sometimes they'll be down there and they're in like a lack of heat, a problem job. And they just want to like increase the flow rate or whatever. I'm like, do you know how much more pressure drop that's going to cause by increasing just a little bit? You think you're going to double the flow, you're going to quadruple the head loss. The pump that you have has no capability, no chance of doing what you think it's going to do, but it's only because, again, not their fault. They're just not aware. This is the relationship of the change in flow and the corresponding change in head. It's a squared relationship. So what it would look like on a graph or on a pump curve is they might call this, and again, pressure drop, friction loss, and flow rate relationship is the system curve. So you have a pump curve, manufacturer makes pumps. He tells you what's the flow in the head capabilities. And then there's the system curve. And the pump curve and the system curve will eventually intersect and that's the point of operation. And so what they're trying to show here is, and you hear different expressions, but like a ski jump, some guys will call it a hockey stick, and it's kind of a low grade, and then it just takes off. That pressure drop just really rises as that flow rate increases in that existing system. So once you have a known flow and head, any other change, we know exactly what that new head loss is going to be. We can calculate it. Because now take it to the extreme. Go into variable speed pumping. You enter a large building, you got a 100 horsepower motor, and he's moving X. And then all of a sudden, a bunch of the fan coils throughout that building start to close down. And we're sensing this buildup in pressure with these VFD drives, these remote sensors. And they feed back and they say, whoa, back down. You don't need to do that. So now as I start to reduce the flow, the head is a squared relationship, but the power consumption is a cubed relationship. So now I really drop my horsepower load. So now I drop my KW consumption, which is the whole drive, the whole reason why utilities offer commercial buildings incentives to add drives to their buildings, to their existing pumps. You know, the older technology, upgrade it, put a drive on it. You can save electricity. You can save load. So anyways, there's this relationship. And here it is, kind of a big picture, system curve construction. Now, all we're saying is, depending upon if you know the original flow and the original head, you're saying, hey, I want to change it. I want to increase it. I want to decrease it. Whatever that relationship is, square it times the original becomes your new pressure drop. And we'll go through some different examples, whatever. This is saying, hey, I know I need 200 gallons a minute and I'm overcoming a certain pressure drop 30 feet ahead. I can calculate any other change in flow and what the corresponding pressure drop is going to be. Let me see here. Do I have it? I don't think I have it. That system sizer, again, we're not going to do that tonight, or at least not right now, but just be aware. And it's kind of a useful scale. And when people see it for the first time, it can be a bit challenging, but this scale here is based on that formula that I just showed you. And then the only reason I just want to point it out is they have feet of head on the top side and they have PSI on the bottom side. And the way you could use it is you could say, I do that, yeah. You could say 200 gallons a minute on scale 5 at 30 feet ahead. And what would happen is you'd line up those two sets of conditions, 200 gallons a minute in this white band here, and you'd find feet ahead. So I'm finding 30. So I'd line these two guys up. And then just real quickly, if you do bother to look at it, one of the examples they said was, hey, what happens if I move 230 gallons a minute in that system? Well, without moving the wheel, just look, find 230 and then read straight up. And the answer is 40. So it's doing that math formula. The guy who developed this was that Gil Carlson. He put together this wheel for himself, selfishly, a long time ago. It was made of cardboard. He made it at home. And he brought it to work. And he was in his office at Bell and Gossett. This is going back years ago. And he's in his office. He's got a cigarette going. And he's got the wheel. And he's doing this. And one of the marketing guys from Bell and Gossett walks by his office. And the door's open. What the hell is that, Gil? What are you doing? And he said, oh, just, I got all these calculations in these booklets all over the file cabinet. I just wanted to make it easy for myself to be a little quicker. So we made this wheel. So the marketing guy said, we can market this. And they took it and they put it on this plastic wheel. And there's tens and tens of thousands of these all over the United States and Canada. But so it does a bunch of different things. But this scale 5, which is all about the relationship of flow and the change in pressure drop, is pretty useful. Today, you got an app. Go to the App Store, go to Apple. You can download the B&G System Sizer. You can get online. There's an electronic version for like your computer at your workstation or whatever. And you guys probably have all kinds of software. There's so much of it out there nowadays. It's not that big of a deal. But it's funny. The younger guys, they'll load it up on their iPhone or whatever, or their iPad and go out in the field. I'm just too old. I always just bring my wheel with me when we're out troubleshooting something. But anyway, so you got the system curve, and you're building a system curve here, 200 gallons a minute at 30 feet ahead. That's what we're chasing, and so we plot a couple different conditions. And then we want to buy a pump. We want to select a pump that ideally can meet that set of conditions. Sometimes it happens. A lot of times it does, but sometimes it doesn't. And we can talk a little bit about that. But anyways, so the pump curve is manufactured. That's what the pump manufacturer can create based on an impeller diameter, speed, RPM, and horsepower. And then the system curve is the known set of conditions. And as you change flow in that given system of 200 at 30, I know what the new flows and what the new pressure drops will be in that system. And we don't need to get into that right. Well, I guess maybe just real quick. You're into like a cooling tower. So you have some static. Now it's not closed, so to speak. You have elevation that you got to account for. So you have this closed, so to speak, or this pressure drop, this frictional resistance, but you have this 10 feet that is a given. It's never going to change. You've got to lift the 10 feet. You got to overcome that. So when you start building curves or system curves, you don't start down here at 0. You start at 10 because that 10 never goes away. As you change the flow, increase or decrease, the pressure drop's going to increase or decrease accordingly, but the 10 feet never goes away. You still always got to overcome that 10. Kind of some standards, industry standards, fluid head loss in feet, how much over a given distance, the rate of head loss measured per 100 feet of equivalent straight length of pipe, industry standard. So it's giving us a quick example, whatever, just numbers. But here's the thing to take away, and we'll repeat it, and you've probably already seen it, and probably some of the software back at your firms already account for this. And ASHRAE has some charts and tables and such, but typically a friction loss, no greater than around 4 to 4.5 feet per 100 feet is a pretty safe number. 100 feet of pipe selected for the certain flow rate you're moving will not experience more than around a 4 to 4.5 feet of head loss, energy, friction, and resistance for every 100 feet of equivalent straight pipe length. So the reason why I highlight that real quickly, equivalent is fittings. You got to account for fittings. So they'll refer to them as, excuse me, before I get to fittings, here's just a standard. They're talking about pipe size, pressure, flow rates, friction loss, how many hours does the pump operate? And they'll get into these different standards, and you'll see that a given size pipe, as the hours increase, the energy consumption would be greater. So they start to say, hey, 180 is dropping down to 140, maybe dropping down to 110 from an energy consumption. What's going on? So again, I just pulled out of one of the ASHRAE fundamentals back in 2021. But the fittings, what they're talking about here is equivalent length. So the length of pipe of the same size as the fitting that would result in the same pressure drop as the fitting. So we highlight it real quickly here, but 2-inch, welded or side T branch is what they're saying here is 5 feet. So that particular fitting would offer an additional 5 feet of pipe length for the pressure drop flowing through as if it was straight pipe. So all of these things come into account. All the software accounts for fittings when you're designing a system from scratch. This little sheath, which again, it kind of reveals the age of it, but they would have fittings, steel and cast iron fittings, 2-inch through whatever diameter, all the different fittings and what the TEL, what the equivalent length would be. When you're out in the field and you're troubleshooting and you're kind of working with existing stuff, a rule of thumb that the industry has used and continues to is add 50% of straight run. I got 100, I go over 50, I come back 100, another 50. Okay, 1, 2, 300 feet of pipe times 1.5. Right? So that's another 150. I got 450 TEL. That's how I'll calculate my pump head. Sometimes oversized, but it's a pretty safe number. But when you're engineering from scratch, you're going to account for all of this in your design. Again, just other components we talked about, known pressure drops. The manufacturers of all these different components, they're published, they're available, what that pressure drop will be at certain flow rates. Simple little drawing, again, very simple, but series piping versus parallel piping. What's the system pressure drop? Determine the total pump head. So in series, whatever the pressure drop was of these various terminal units, it's in series. You're going to account for that. It's going from one to the next, to the next, to the next. Now you take it and you lay it out a little differently and you call it in parallel. So this pump is feeding this in parallel with this, in parallel with this. I don't have to add all of that pressure drop up. What the pump's responsible is the total flow of all of these individual loads, but the pressure drop of the greatest circuit. All things being equal in this very simple drawing, it would be the distance, the furthest run. If all four terminals were the same and they're receiving the same flow rate, so same pressure drop, I need to overcome the pressure drop of this longest circuit. And if that pump can develop the head for that, it can certainly develop enough pressure differential for these shorter runs. So when you have like parallel circuits, it's the pressure drop of the greatest or the longest. Sometimes that's the answer, but it's the total flow of all of the circuits. In series, it's seeing each other. It's in series. You're adding up each one. So anyways, so you're looking at a pump curve. It's an old B&G, well, I shouldn't say old, E1510. That's the modern the newer version. But that's, probably a printed version in a catalog. You guys are going to see it online, most likely on software. So it's a 1510, E1510, 2.5 BB, 1750 RPMs. A lot of information going on there. It's like pretty. Bleh. So you start breaking it down. You say, okay, impeller diameter and performance curve. So 9.5 is what you'd say, that's the full wheel. Remember I made that statement earlier. That's the max diameter I can put in this particular model. The manufacturer can. They've determined that. They've tested it. And then I can trim it, usually in 1/8 inch increments, but they're showing them in whatever, 1/2 inch increments as far as 9.5, 9, 8.5, 8, 7.5. So they're just showing the performance curve. So what the pump can do at these different diameter impellers. Start looking at these lines here. They're representing the constant motor horsepower lines. What horsepower do I need for that set of conditions, that flow and head? So impeller diameter and pump performance curve, horsepower curves. You'll hear the expression best efficiency point, or BEP. When you go to select a pump for your particular needs, ideally try to keep it somewhere within this BEP range is what they're trying to highlight here. And then the manufacturer has these efficiency lines of constant pump efficiency. So, there's a range. It's not like it has to be right here, but typically if you start going outside it, you start to affect pump performance or pump life. There's another curve that they kind of sits off to the side here, but called NPSHR. NPSHR, so net positive suction head required. So the manufacturer, when he manufactures the pump, he's saying, hey, I know that for water to stay water and not to flash, to cavitate internally in that pump, that water's got to have a certain amount of head, pressure, so that it stays water, it doesn't drop. And so they test it and they publish it. And if you notice, the greater the flow rate, as that flow rate increases, the required, because you think about that impeller, we showed the drawing earlier, the picture earlier, but you got a certain diameter on that eye, right? As that flow rate gets greater in that given fixed eye, the pressure drop goes up. And that's all is reflecting right here in this statement of this curve, is as you try to shove more flow through my impeller, my required NPSH starts to go up. You got to be aware of that. Closed systems, they're filled or pressurized, it's fine. You get into open systems, you want to be aware of it. You get into high temperature, you ever sat dealing with condensate, like in steam systems, hospitals, and you gotta design a condensate pumping mechanism or system. You want to be aware of temperature and elevation and all of that. But it's mainly just to break it down. We got pellet diameters, pump curves. We've got horsepower curves. We've got efficiency curves. Now we've had this last thing here, NPSH curves. Um, yeah, really. I mean, is that pretty standard? Lower, correct. Yeah, correct. Right. Yes. And that's probably pretty standard across, take that name away and replace it. It's just pretty standard. It's the nature of the design of the volute and economics and then cost and blah, put it all together. What this was, what I was getting at is, that's that pump curve, the complete pump curve. But do you want to pick a pump, way out here or maybe way back up on its curve? And that's what they'll talk about is, preferably or acceptable ranges are the same. Whatever the BEP is of that particular pump, you have a range, a good practice, best practice, good practice, industry standards would be left of that BEP around 15% would be considered best. But what's pretty standard and acceptable is up to about 30% or so left of BEP. And then if you moved to the right of BEP, about 15%. Best practice would tighten it up a little bit, but it narrows your selection. Um, but what all the manufacturers of the pumps are saying is, as you move left of or right of, what is it doing to the pump conditions? Like suction recirculation, low impeller life, low bearing seal, low flow, some of the conditions that will happen as you could select it and it will run. It just might not be the best selection for longevity. Go the other way and you start to move way out on its curve, low bearing, low seal life, potentially cavitation. If you think about that cavitation, we talked about that as the flow rate increases. So as you move out on that curve, the required NPSH starts to climb. If you don't have it, the pump will cavitate and start to beat itself up. So they're saying, as you get into this field and you start selecting or you continue to select, just be aware of some of the ideal ranges that you want to make your pump selection for longevity. Yeah, ANSI, HI here, they're just, what they're referring to here is, I mean, pretty specific speeds, but they're getting into less than 4,500 RPM speed. Preferred operating range between 70% and 120 of BEP. So whatever your BEP is, about 20% to the right of it and 30% to the left, which kind of was picked out here a little bit, 34% less. So 30% less is 70. And then 15% or 20% is 120% of BEP. So that's pretty standard stuff. We're not getting into any of these other ranges of speed typically. So anyways, something to be aware of. I don't know if you have a further comment you want to make on that. Safety factors. History, right, right. Design conditions, right, 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 right. What do I want to do here? Just talking about some of the different RPMs, 1200, 1100, 1200 RPM, and what the application typically would be as far as from motor selections, high head, low flow, cooling towers, may low. When I talked to you earlier about condensate pumps, where you're dealing with some low head capabilities or hot temperature, high temperature condensate, low NPSH. This is the majority. That's why it's kind of highlighted. 1750, 1800 RPMs is pretty standard. 50 hertz. Yeah. Knowing you got to see the 50 hertz. Right, 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 right. We'll just kind of touched on this real quickly, but just a quick example of when you're selecting the pump, and again, back to software, they give you all the different options. And I apologize for some of the clarity, but up here it's talking about the flow rate, total system flow. So someone calculated they need 475 gallons a minute. And the pressure drop was going to be 65 feet ahead. So 475 at 65. And then when you get into the motor settings, one of the options they can say is, hey, select it based on duty point. The set conditions, 475 at 65. And you kind of go through and it's saying, hey, I need duty point 9.57 horsepower, brake horsepower. So I'm going to select a 10 horsepower motor. So then I spit out a pump curve, off of that software selection, and it's saying, hey, here's the conditions. 475 at 65. Here's my curve, whatever that diameter is of that impeller. Here's the dash lines right here. That's the 10 horsepower motor. It's fine. It's below the 10 horse. It would work. It absolutely would work at duty point. What we're starting to refer to is sometimes if that 65 feet ahead doesn't exist, meaning the pressure drop that we calculated, maybe it's not quite as high as we thought it was. And so now it's somewhere down in this range here. Well, that pump doesn't know that necessarily. Now we get into variable speed, ECM and some smart technology. But generally speaking, what would happen is that pump might slide out on the curve because the resistance isn't there. So then all of a sudden you're overloading the 10 horsepower motor and you're having some problems. So when you go back to your original selection, one of the options would be to say, hey, yeah, 475, 65 feet ahead, motor selection. Can you pick me a non-overloading motor so that across that whole impeller curve that I've provided in this particular pump to meet the 475 at 65? So then what happens is down here, the motor horsepower is 15 that it selects for non-overloading. It's Yeah, right. As far as the different firms, they'd probably build that in to protect. So there's still the brake horsepower is a 9.75, but across the total curve, so that dark line is the impeller curve, and it passes the 10 horsepower, but it's well below the 15. So that would be referred to as non-overloading across the entire length of that curve. You're never going to overload the motor. You're never going to overheat it. You're never going to create, maybe it shuts down on heaters or whatever that protect the motor and shut it down because it exceeded. So you have options. And to Will's point, probably the software selection you guys are using might already have that built in, that they say, hey, we're going to go to non-overloading perhaps, for general cooling and heating, closed loop applications where there's, dozens or hundreds of fan coils or whatever the terminal units are, and those flows are constantly changing and opening and closing. We want to protect. So anyways, specific gravity, you guys can teach me. Pretty easy, but always references. If you're dealing with something other than water, what is it that becomes a specific gravity and how it can affect pump head, foot-pounds per pound. So, if it's something other than water, if it's water, it's 2.31 divided by 1 is 2.31, period. But if you're dealing with either glycol or something like that, it could impact. I just had one last thing I just want to show you. Like, this is showing 60-degree water, 100 foot. If I had a gauge at the base, I'd be reading 43 pounds, of static height. If the specific gravity, if I was using 230 degrees, well, technically it's a little bit less than 1, it's 0.95. And so to actually read 43 PSI at the base, I would have 104.5 feet of head to provide that same 43 pound static pressure, if you will, looking at static pressure. And then the last thing was, if you had, ethylene glycol 40% mixture, the specific gravity is 1.07. So actually, I'd only need 90 or only have 92.8 feet of to represent on this gauge, this pressure gauge, 43 PSI. I think one last thing, we'll just go through this real quick, and again, we can reference it. But what it's talking about is why the pump manufacturers typically will list their pump curves in feet as opposed to PSI. So when you open up ours or any of the manufacturers, it's always the flow rate on that horizontal axis and the vertical's feet ahead. It's not in PSI. And it's just so that regardless of what's happening, that pump curve is accurate. So all they're saying here is pump delivering 30 feet head at whatever that design flow rate is with 60-degree water. So back to, basics, behind the scenes, what the software is already doing for us. The weight we talked about, the density, 62.3 pounds per cubic foot for 60-degree water, divided by those 144, the square inches per square foot is 0.43 PSI. So if I had 30 feet times 0.43 would be 12.49. So as a tech out in the field, I might put gauges on the pump because I want to know what the pump's doing. What is he actually doing? There's no meter here saying, hey, I'm pumping 400 gallons. So they'll use the gauges across the suction and the differential, and they'll look at a pump curve. So in this set of conditions, I would read a 12.9 differential. So in this case here, I'd have a gauge, maybe my suction's at 80, my discharge would be 92.9. I subtract that, there's my 12.9. 12.9 times 2.3, there's my 30 feet. I can look at the pump curve and say, hey, X number of gallons a minute, overcoming 30 feet. If I had 300-degree water, not 60, now all of a sudden my density is not 62.3, but it's 57 point. So there's a subtle difference. Not huge, but there's a difference. And you start doing the math, and all of a sudden, it changes a little bit. But at the end of the day, you're multiplying that differential, that 12 times that new calculated 2.5 feet per PSI because of the density change. So I still have my 12 PSI, but more importantly, I have my 30 feet on my pump curve. So the manufacturer is still referencing X number of gallons a minute at 30 feet, regardless of the density. So it's going to show up in a difference in the gauge readings because of the densities. But instead of having to have different pump curves for different densities all the time in PSI, they put it in feet, and then you convert it based on your density of the water that you're using. I don't even know how relevant this is, Will, anymore, but flat versus steep, and with VFDs and all of that. But what they would have referenced is if you're picking pumps, so you're picking a flat curve, a flat style curve versus a steep style curve. And the way they defined it, flat versus steep, is from the BEP to shut off or no flow. They call it no flow. When that pump backs up on its curve to no flow, 0 GPM maximum pressure differential, it only increases about 20% from BEP, excuse me, less than 20% from the BEP. They'd classify it as a flat style curve. And then anything that flow to no flow, that head developed greater than 20%. So as I backed up from BEP, that would fall into the category of a steep curve. Yep. Right in. So it's so.
You see duty points at a B. It says 200 gallons a minute. It's really operating at 8, or vice versa. It's double dipping in power. You'll see sometimes flat. So the whole point is you are doing larger circulators. Shy with very, very.
Has a question. What makes it that flat over curve? Is it the shape of the impeller base?
It would be the housing. How would you?
Yeah, combination of the impeller, you know, the shroud, how wide or how narrow, the diameter, narrow or smaller, right? A smaller diameter, probably wider, is more of a flat style versus get into a higher head pump. It's a larger diameter and probably a little narrower on the shroud itself. So no. Let me see here. I think we got one last thing here, just saying minimum required flow. All they're saying is when you're picking in somewhere in that best efficiency range, BEP, the industry would have some, hey, what's my minimum flow to the pump? How low can I back it down to? What's an acceptable range or suggested range, percentage of? So in this case here, we have a pump, a base mounted pump. We've got 280 gallons a minute. And what we're saying in this category here, single suction, flow rates greater than 100, under 800, figure about 20%. So 20% of 280 is around 50, 55, 60 gallons a minute, somewhere in there. So that would be, I really wouldn't want to go any lower than that from minimum required for the pump manufacturer. So again, just little ranges that you want to work in, but typically, to Will's point, you're somewhere in that BEP and probably a little bit right of it nowadays with the technology. This is just a quick example why we'd be using those triple duty valves. Been a long first day.
Wasn't so long. I thought we were until 10.
Sorry to disappoint. Thank you all very much. Hope you survived, or hope it was okay. Please take those manuals home with you. They're yours to keep. We'll be in touch with you through an email with the PDF version of what we talked about tonight. There will be a link also for the manual, so if you want to have one to download them to like a computer or something,
instead of having just the paper copy, they're all existing as well, so both will take care of that. And I guess without wasting any more time,
Thank you, George.
we'll see you next Wednesday. All right, have a great week, and a great weekend. Yeah. Oh, do you guys have that signed sheet of the?
Yes, it's over here.